Hello everyone, this talk is about graph neural network bandits. To our knowledge, this is the first work that connects powerful graph neural network models with bandit optimization. My name is Ilija Bogunovic, and this is a joint work with my collaborators Parnjan Kasrai and Andreas Krause. Learning on graph structured data such as molecules, materials, or biological graph representations requires designing sequential methods that can effectively exploit the structure of graphs. So consequently, graph neural networks, or GNNs, have received attention as a rapidly expanding class of machine learning models. They deem remarkably well suited for prediction tasks in applications such as designing novel materials, drug discovery, structure-based protein function prediction, and many others. So this raises the question of how to bridge the gap and design bandit optimization algorithms on graph structured data that can exploit the power of graph neural networks to approximate a graph reward function. So in this paper, we consider bandit optimization over graphs and propose to employ graph neural networks to estimate the unknown reward. Now, a little bit about the formal problem statement. We consider a bandit problem where the learner aims to optimize an unknown reward function via sequential interactions with a stochastic environment. So in particular, we assume that we are given a finite set of graphs, with n being the number of nodes in each graph. Our objective f is unknown and is a graph function defined over the domain set of graphs. As an example application, consider drug or material design, where molecules may be represented with graph structures, and the reward f of g can correspond to an unknown molecular property of interest, for example, atomization energy. So at each time step, we choose which graph to evaluate and we observe a noisy observation. Our goal then is to minimize the standard notion of cumulative regret, and the goal of the design algorithm is to be no regret, meaning that the total average regret goes to zero as t goes to infinity. This implies that we seek sublinear cumulative regret guarantees for our algorithms. So when it comes to graph representation, we look at the standard scenario where each node is associated with the graph node feature that lies in a d-dimensional space. In general, we can represent each graph as a concatenated feature vector in the n times d dimensional space. As common in the graph convolutions, we also define the aggregated node feature, which is simply a node feature that is averaged and normalized over the node neighbors, including itself. So this is shown in this picture. So lastly, we let P of n be the group of all permutations of length n, and we use C times G to denote the permuted graph. So permuting the nodes of a graph, we end up with a permuted feature vector as shown in this image. Okay, now we have everything in place to define our reward model. It turns out that in many practical problems, the reward function does not depend on how nodes are ordered. So this means that if we are to permute the graph nodes, the function value should remain the same. So consequently, in this work, we assume that the reward function belongs to the RKHS, or reproducing kernel Hilbert space, of a permutation invariant kernel. Any permutation invariant kernel can be written as shown here for any base kernel denoted as k. So in principle here, we simply average over all possible permutations in our group. So to deal with large graphs, that is when n is large, we assume an additional structure. In particular, we assume that our kernel is additive and consists of the sum of base kernels that are defined on the smaller d-dimensional aggregated node feature space. So to sequentially learn and optimize the reward functions of the previous form, we are going to use graph neural networks. This choice is motivated by the expressiveness of GNNs, the fact that they scale well with graph size, and particularly due to the invariances embedded into its structure. So more precisely, we use a GNN architecture with a single convolutional layer and L fully connected layers of width m. So the parameters of the GNN are initialized IID from standard normal, and the precise definition of a GNN architecture that we use in this work is shown in the circled equations. Now we observe that the graph neural network FGNN is invariant to node permutations, meaning that for all graphs and permutations, its prediction does not change if we are to permute graph nodes. And the key step to show this property is proving that FGNN can be expressed as an additive model of L-layer fully connected ReLU network. In this work, we prove a novel connection between permutation invariant kernels introduced before and the GNTK, being the graph neural tangent kernel. In particular, recall the permutation invariant additive kernel and set each base kernel to be the famous neural tangent kernel. Our main proposition then shows that such a permutation invariant additive kernel is the same as the graph neural tangent kernel. This will prove very useful in our analysis later on. The graph neural tangent kernel corresponds to the well-known lazy regime of training graph neural networks. In particular, when the width M is large, it can be shown that during training, for all graphs in the domain, the network remains close to its first-order approximation around initialization parameters. So training this linearized model with a squared error loss is equivalent to kernel ridge regression with an induced GNTK in the infinite width limit. In our work, we consider the following function mean estimator that is obtained by training the GNN with gradient descent on the provided mean squared loss. We also make use of the following uncertainty estimate that depends on the gradient of the GNN at initialization. We note here that both the uncertainty and mean estimators are not quantities that depend on the GNTK, but they only depend on graph neural network that is used to compute them. Our main theorem then states that we can use these proposed estimators to obtain valid confidence bounds for every graph in our domain when the true function has a small norm under the GNTK kernel. This holds when the width of the network is polynomial in all the parameters of interest and under sufficiently small learning rate that's used to train the network. Our main algorithm is called GNN phased elimination. It runs over episodes of exponentially increasing length and select graphs from the current set of plausible maximizer graphs denoted as GE. In particular, at every step within an episode, the algorithm selects a graph with the highest estimated uncertainty. At the end of each episode, it retrains GNN with new data and updates GE by using the novel GNN confidence bounds that we've shown before, as it is standard in ARM elimination bandit algorithms. We obtain sublinear cumulative regret bounds that, in contrast to the standard neural bandit bounds, do not depend on the number of graph nodes and scale only logarithmically with the number of graphs. Finally, we perform some experiments on random graphs and objective functions that are drawn from a Gaussian process with GNTK. Here, we show the empirical cumulative regret as a function of number of samples, as we also increase the number of graphs in our domain set. We observe that GNN PE, given in purple, achieves sublinear rates and is able to exploit the structure in the objective function to outperform all the baselines. If you want to know more about other interesting experiments that we performed, as well as about other theoretical findings, please read our paper or feel free to reach out.